Hello, and welcome to the introduction to the central limit theorem. We're going to start with an example to hopefully help you with the concept. So we have a situation that says X is going to represent the length of time in days that a cookie recipe lasted at the Olmsted homestead. We're going to assume that each of the different recipes makes the same quantity of cookies. So we don't need to be interested in the cookie recipe number, or just the number of days that each recipe lasted. So on day number 1, the batch only lasted 1 day. But the second time they made the batch, it lasted 5 days. The third time they made the batch of cookies, it lasted 2 days, and so on and so forth, all the way through day 60. So what I did was I calculated the population mean using Desmos. You'll see the file in Canvas to be 3.57 days and the standard deviation of the population to be 2.148 days. So this is population data. This is all 60 days. Okay. Then what I had my class do was that my class took 4 samples. Each of the sample had 5 observations. And we calculated the mean for each of those samples. So here are the 4 means. So you'll want to write those down. And you'll want to write down the population mean and standard deviation. Then I had the class take 4 more samples, but each of those samples had 10 observations. And here are the means for those individual samples of size 10. And then don't worry about these yet. Yeah, take these 4 means, then take the average of these 4 means is going to be 3.65, and the standard deviation of these 4 means is 0.3697. And what we notice is that the mean itself does not veer very far from the population mean. So that the mean of all of these averages was 3.65, pretty close to 3.57. However, the standard deviation went from 2.148 days to only 0.3697 days. So the standard deviation between the samples became very much reduced. And so this is what we came up with for the samples of size 5. We had a mean of 3.6, and that standard deviation was 0.816 days. And then, like I said, for the sample of size 10, the mean of the samples was still pretty close to the population mean of 3.65, but the standard deviation was even smaller at 0.3697 days. And so what we notice here is that I can take samples and samples and samples of the batches of cookies. The smaller the number of values in a sample, the less like it's going to be to the population. But the larger the sample I take, the mean stays about the same, but the samples don't vary from each other very much at all because the sample size is getting so large. And so we have these curves that still look normal, but they become really, really, really skinny is what happens. And so because these samples are very similar to each other, we have to offset that when we look at our standard deviation. So what we learned in 6.1 and 6.2, we're now applying to 6.3, except for when we're comparing samples to samples instead of an individual, which is what we did in 6.1 and 6.2. We looked at individuals. Now we're looking at samples. And so when we're looking at how samples compare to one another, our mean is still going to be the same, but we have the adjusted standard deviation, which is called a standard error. Okay, that's going to be called the standard error. And you can see that that's taking the standard deviation and we're dividing it by the square root of n. So as the n gets really big, we're going to be dividing by a little bit bigger number. and it's going to cause the standard error to be quite small because the samples won't deviate from each other very much. Okay. So let's start here at lesson 6.3. So suppose that X is a random variable with a distribution that may be known or unknown. Okay, or unknown. Using a subscript that matches the random variable, suppose the mean of all these samples is the average of the sample means, and the standard deviation of the samples is the standard error here. Okay, so we're going to take the standard deviation of the sample means and divide by the square root of n. This is called the central limit theorem for averages. It says that if you keep drawing larger and larger samples and calculating their means, the sample means from their own normal distribution will be similar to the population mean, and the standard deviation will get smaller and look like this standard error. Now, how do we know when we can use the central limit theorem? And we can use the central limit theorem when we've met these three conditions. So the conditions are random is the first one. We have to make sure that each observation is collected randomly from the population. The second one is independence. We need to make sure that our observations are either collected without replacement. Most of the time, it's going to be without replacement. If it's with replacement, we don't have to worry because then everything's independent. If we are not replacing, so if you ask me a survey question and I answer the survey, I can't answer again, right? So that's without replacement. Then I have to check to make sure that my sample size, the little n, is less than or equal to 5% of the population. So I'm going to show you how we will explain that. And then the condition 3 is normality. We have to prove this. And with quantitative data, that's means right here, we're doing in 6.3, this can be shown by either I tell you that it's a population that is normally distributed, or I give you a normal probability plot, or I am going to tell you that the sample size is large enough and it's greater than or equal to 30. Okay. And I showed you that normal probability plot in lesson 6.2. So if we can say that we've met these three conditions, then we can describe our population, describe our distribution here. And we can say that our shape is approximately a normal distribution, and the mean of the sample means is going to be approximated by the population mean that we know. And then the standard error of the sampling means is going to be by taking the population standard deviation and dividing by the square root of n. And if we have sample data, this would be X bar. And then if we have sample data, this would be S divided by the square root of n. Okay. So let's jump into some examples. Much of this lesson is going to be building and using the same techniques, especially the same ALEKS techniques that we used in 6.1 and 6.2. We're just using the idea of now we are comparing samples to samples instead of individuals. Okay. So example 1 says unknown distribution has a mean of 45 and a standard deviation of 8. Samples of size n equals to 30 are drawn randomly from the population. Find the probability that the sample mean is less than 42. So I'm not really at this point worried about my central limit theorem. However, I do want to find the probability that the sample mean is less than 42. And so because I am comparing the sample mean, not just one single observation compared to a mean, it's the sample mean, I am checking to see what my probability that the sample mean, X bar, is less than 42. Okay, so we're going to draw where our typical sample mean is, or typical population mean is at 45. And so that means I'm going to say 42, and I'm going to shade this in, and I'm looking for this probability. And so we're going to do exactly what we did in lesson 6.2, and that's finding the z-score for this. Okay, so it's going to be 42, subtracting 45, divided by not just the standard deviation, but the standard deviation of 8 divided by the square root of 30 for the sample size, because we have to use that standard error. Okay, so let's practice this in ALEKS. And we are going to take here and say 42 minus 45 parentheses divided by 8 divided by the square root of 30. And there's our standard deviation, a negative 2.054. And then we're looking for the probability of z less than that standard deviation. And I won't be going back and forth to my paper as much because we're testing to see if we can know the steps. I will show you my paper at the end of each problem. This is very much similar to what we did in lesson 6.1 and 6.2. So 0.01999. So this is what we're looking for. We had to standardize that by calculating the z-score. And then once we calculated the z-score, we looked for the probability that z was less than that z, and that came out to be 0.0199. Example 2. The length of time taken on the SAT for a group of students is normally distributed with a mean of 2.5 hours and a standard deviation of 0.25 hours. The sample size of 60 is drawn randomly from the population. Find the probability that the sample mean is between 2.49 hours and 2.58 hours. So 2.5 is our mean right there. So 2.49 and 2.58. Is this right here. So remembering what we did back in the last 2 lessons is we are going to take the difference here. We're going to find the probability that X, the sample mean, is less than 2.58. And we're going to subtract that from the probability that the sample mean is less than 2.49 to find the difference. But we have to standardize that first. So we're going to find each of those z-scores, and then we're going to find the difference. We're going to find their probabilities and subtract the probabilities of those z-scores. Okay, so let's go to ALEKS to do that. Hopefully you have your ALEKS pulled up as well. And so we've got 2.58 subtracting 2.5 divided by 0.25 divided by the square root of 60 was our sample size. And so the first z is 2.4787. And I'm just going to hit the probability less than that right now so I can get that probability. So that probability is 0.9934. And then I'm going to undo. And everything here is the same to find the other z-score, except for I'm just changing this sample mean to be 2.49 hours to take the SAT. I'm going to find that z-score is a negative 0.3098. And I'm just going to hit my probability of z less than that and hit enter. And that z-score, I'm sorry, that probability is 0.3783. And then I'm going to take my first probability, 0.9934, and subtract my second probability of 0.3783. And there is the likelihood of being between the two. And of course, I'm going to share my paper so you can see all the work that we've done together. And let's just interpret this together. So approximately 61.5% of students take between 2.49 and 2.5 hours on the SAT. Example 2. So let's move to example 3. Example 3 says, based on data from the National Health Survey, women between ages of 18 and 24 have an average systolic blood pressure of 114.8 with a standard deviation of 13.1. Systolic blood pressure for women between these ages follows a normal distribution, so that's good. If one woman from this population is randomly selected, find the probability that her systolic blood pressure is greater than 120. Okay, so we are talking about a single woman. So this is going back to lesson 6.2. Let's just write that down. Single woman. So in that case, we are just saying that that individual X is normally distributed with a mean of 114.8 and a standard deviation of 13.1. We don't have to use the adjusted standard deviation because it's a single woman. So we're looking for the probability that X is greater than 120. And so to do that, we have to find the Z that goes with 120. So let's go ahead and calculate that. So we have 120 and subtracting the mean, 14.8, and dividing by 13.1. We don't have to worry about the sample size because the sample size is 1. So that Z-score is 0.3969. And because it's greater than, we have to do 1 minus the probability of the Z-score being less than. So I'm just going to adjust that here. And I'm going to copy that and say 1 minus that. And I'm going to delete this. And then, so I'm using a complement. So my probability is 0.3457. I'm going to show you on my paper. So it's greater than 120. So this is what we were looking for. This is for normally distributed. That's what the probability we're looking for. This is our adjusted normalized Z-score value. We had to, because it's a greater than, we had to do the complement. And so there's a 34.57% likelihood of this happening. Part B, if 40 women from this population are randomly selected, find the probability that their mean systolic blood pressure is greater than 120. So now we want to know about the group. Okay, so what is the probability that the sample mean is greater than 120? So that means our adjusted Z-score, our normalized score is 120 minus 114.8 divided by 13.1, and that has to be divided by the square root of 100 of the 40 women. So let's look at our Z-score for this. And 20 minus 114.8, that looks the same. Divided by 13.1, that looks the same, but now we're going to divide by the square root of our sample size. So this Z-score is 2.5105. And it's still a greater than. So we have to do the complement of 1 minus the less than. So 1 minus the less than of 2.5105. And this is not very likely. Very small probability. So it was a high probability for an individual, a single woman, to have a blood pressure higher than 20. But if you take a sample, samples are going to be pretty close to another sample to another sample. And the likelihood of that sample having an average of 120 or more is very small. And that would be considered unusual because it's less than a 0.05. Okay. And we're thinking about what's unusual because when we start doing hypothesis testing in chapter 8, we have to know what's unusual. Okay, so C says if the sample were 4 women between the ages of 18 and 24, and we did not know the original distribution was normal or not, could the central limit theorem be used? And we would say no, and that is because a sample size of 4 is too small if we don't know the distribution. Okay. Example 4. Example 4, steps. A study was done about violence against prostitutes and the symptoms of the post-traumatic stress that they developed. The age range of these prostitutes was 14 to 61. The mean age was 30.9 and the standard deviation of 9. We're going to verify to see if these 3 requirements were met. So the first is, do we have a random sample? And I guess we didn't write there the sample size. If you look at part B, it says in a sample size of 25 prostitutes. So we're going to say the sample is 25. So the sample, we will assume it's random. It doesn't say. We're going to assume that. Shouldn't always assume, but independence. We want to see if 20 times n is less than our population size. So 20 times 25 is equal to 500. And we would assume, unfortunately, that there's probably at least 500 prostitutes in the US at this time. Unfortunately, that's not a healthy way to live. But we probably can assume that they are. And then 3 is to show that our distribution is normal because we don't know anything about our distribution. And our sample size is equal to 25, which is less than 30. And we don't have a probability plot. So technically, no, we cannot use the central limit theorem, the CLT. That's how we would prove that. But we are going to use it anyway, in this case. Okay, so let's say we do have a sample of 25 prostitutes. What is the probability that the mean age of the prostitutes is less than 35? So what is the probability that the mean age is less than 35? And the sample mean has been 30.9. And so 35 is right here. I'm guessing there's a pretty high percentage that is less than that. We need to normalize that by finding the z-score. So that's going to be 35 minus 30.9 over standard deviation of 9 divided by the square root of 25. That is so we have 35 minus 30.9 divided by 9 divided by, we know the square root of 25 is 5, but I'm just going to put it here so I can see the formula. And that comes out to be 2.278. And we're looking at a less than, so it's the probability that the z is less than 2.278. And we can just click on that probability and it will fill it in and hit enter. And that is a very high likelihood of 0.9886. So very likely. Very likely that they're less than 35. Let's look at part C. Part C says, is it likely that the mean age of the sample group could be more than 50 years old? Well, let's get him up there. So 50 is going to be way up here if the average is at 30.9. So what is the probability that the sample mean is greater than 50? So we have to find the z for that, and then we're going to find the probability of that z being bigger because it's a greater than, so those have to match. And that means we are doing the complement of 1 minus the probability of z being less than. So let's find our z with that. I'm going to undo. And we just have to go up here and put 50. Ooh, that z-score is so large. We can almost guarantee it's going to be unusual. So I'm going to put that in that probability, and then I'm going to just write in the complement 1 minus. And yeah, it's so small, it pretty much comes out to be 0. So it says interpret the results. Almost a 0% likelihood that the sample mean would be more than 50 years old. Part B. Find the 95th percentile for the sample mean age of 65 prostitutes. Excuse me. So, this one is a little different. 95th percentile means that we have 0.95 here, right? And then a little 0.05 here. So we want to find X of that. So the first thing we have to do is work backwards, which means we have to find the Z of 1 minus 0.95, which is Z of 0.05. And that's going to be 1 minus 0.95. And so that Z is 1.645. And so let's go back to our paper. You have to remember how to do this, right? So if we go back to our notes and we want to find an X value, the X value is going to be the Z score times the standard error or the standard deviation plus the mean. So we have 1.645 times that 30, the standard deviation of 9 divided by the sample size of 65 plus the mean of 30.9. So let's go back and do that in Alex. So 1.645 times 9 divided, times 9 divided by the square root of 65 plus the mean of 30.9 is 32.74 years old. So it looks like 95% of the prostitutes are going to be 32.74 years old or younger. 95% of the prostitutes would be expected to be 32.74 years or younger, because a percentile is always less than. Examples left here, it says, the cost of unleaded gasoline in the Bay Area once followed an unknown distribution with a mean of $4.59 and a standard deviation of 10 cents. 16 gas stations from the Bay Area are randomly chosen. We are interested in the average cost of gasoline for the 16 gas stations. The distribution to use for the average cost of gasoline is. And so we are not talking about a single gas station. We're talking about a sample of 16. And so we would be $4.59 would be the mean. And then we have the standard error of the standard deviation divided by the square root of n. So that would be B. And the last question says, Never Ready Batteries has engineered a newer, longer lasting AAA battery. The company claims this battery has an average lifespan of 17 hours with a standard deviation of 0.8 hours. Your statistics class questions this claim. As a class, you randomly select 30 batteries and find that the sample mean lifespan is 16.7 hours. If the process is working properly, what is the probability of getting a random sample of 30 batteries in which the sample mean life is 16.7 hours or less? Okay, so if the mean is 17, what is the likelihood of being less than 16.7? The probability that the mean is less than 16.7. If the process is working properly, what is the probability of getting a random sample of 30 values in which the sample mean is 16.7 hours less? Is this company's claim reasonable? Okay, so that means we have to first find the adjusted z-score. 16.7 minus 17 over 0.8 divided by the square root of 30. So that is 16.7 minus 17 divided by 0.8 divided by square root of 30 is a standard deviation of a negative, or z-score of a negative 2.054. And then it's a less than, so we want the probability of z being less than that negative 2.054. So I can just hit the less than button and enter. And that likelihood is 0.01999, which is less than 5%. It's very small likelihood. Very small likelihood. So not likely to happen. And that concludes lesson 6.3. Catch me back for lesson 6.4. We're going to talk about qualitative proportion data.